Hello everyone, my name is Sudheer Kumar, working as an assistant professor of mathematics in MLR Institute of Technology. Last lecture we have seen how to find the eigenvalues and eigenvectors. In this lecture we are going to find power of a matrix by Cayley-Hamilton theorem. Last class we have seen the statement of the Cayley-Hamilton theorem, that is, every square matrix satisfies its own characteristic equation. So in this lecture we are going to cover the topics power of matrix by Cayley-Hamilton theorem and diagonalization of a matrix. Let us find the characteristic equation of this matrix, which is dimension is given as 3 by 3, and find a power 4 by using Cayley-Hamilton theorem. So what is the Cayley-Hamilton theorem statement? Every square matrix satisfies its own characteristic equation. So first let us find the characteristic equation, which is given by determinant of a minus lambda equal to 0. On expanding this, we get determinant of a minus lambda equal to 0. So we get, this is the equation, characteristic equation, right? So by using Cayley-Hamilton theorem, it satisfies its own characteristic equation. So we have to find the power of matrix a power 4. So let us see. So here, since it is satisfying, we have to replace lambda with a. So we get lambda cube minus 6, a cube minus 6a square plus 9a minus 4i equal to 0, right? From this equation we can write a cube value as like this. Now we are supposed to find a power 4, means you multiply with a both sides. So we get a power 4 value is this. So first let us find a square value and a cube value and substitute in this equation. We get a power 4 value. We know a value, so we have to find a square and a cube. So a square, so this is the equation we have to substitute a square value, a value and 24i. So this is the value of a square and this is the value of a, and 24 into identity matrix of size 3 by 3. So on expanding this and simplifying, we get the result a power 4 value. So this is how we find the power of a matrix. Suppose if you want to find a power 7, so what is the characteristic equation we got? This is of degree 3. So if you want to find a power 7, we multiply with a power 4 both sides, so that we can get a power 7, right? Next, coming to diagonalization. For any matrix, diagonalization of a matrix means it refers to the process of transforming any matrix into diagonal form. Diagonal form means only diagonal elements will be there, remaining all elements will be zeros, isn't it? This is a what we call diagonal matrix. So we have to transform the given matrix into this form, so that the given matrix can be said to be diagonalizable, right? So D is equal to P inverse into A into P. We have to find the matrix D such that P inverse into A into P equal to D. Here what is P? P is called a modal matrix, means write corresponding eigenvectors x1, x2 and x3. This is called what we call modal matrix. If there are 3 eigenvalues, for each eigenvalue we find eigenvector. Those eigenvectors, if you denote with x1, x2, x3, write in a matrix, that is called modal matrix, which is denoted with P. After finding the P, you know how to find the inverse of a matrix, P inverse, right? So finding P inverse, then multiply P inverse into A and result matrix you multiply with P, so that I have to get diagonal matrix D. Then only we say that the given matrix is diagonalizable, right? Let us see for an example. If A equal to 1 0 minus 1 1 2 1 2 2 3, find the diagonal matrix D of the matrix A using diagonalization of a matrix. So first let us find the eigenvalues and corresponding eigenvectors. Last class we have seen how to find the eigenvalues of the given matrix. So which is given by, this is the characteristic equation to find the eigenvalues. Characteristic equation, determinant of A minus lambda equal to 0. On simplifying this matrix, we get 3 eigenvalues, lambda equal to 1, 2, 3. Corresponding to lambda equal to 1, eigenvector, let us denote it with x1. Corresponding to lambda equal to 2, the eigenvector is denoted with x2, and corresponding to lambda equal to 3, the eigenvector is denoted by x3. So let us find those eigenvectors. First, corresponding to lambda equal to 1. So A minus lambda I into x equal to 0. In that, substitute lambda equal to 1, so that we get this matrix. Multiply this with x1, x2, x3 and equate to zeros. So on solving this, we get 3 equations. By solving this, we get x1, x2, x3 values, which are in terms of this. So 1 minus 1, 0 is the eigenvector corresponding to lambda equal to 1. Similarly, we can find the eigenvectors corresponding to lambda equal to 2, which is given by x2 equal to minus 2, 1, 2, and corresponding to eigenvalue lambda equal to 3, we get the eigenvector x3, 1 minus 1 minus 2, right. After finding eigenvalues x1, x2, x3, we have to find the matrix P. This P matrix is called modal matrix. This is the first eigenvector, second eigenvector and third eigenvector. Write down all the eigenvectors as columns in the matrix. We denote it with P, which is called as modal matrix, right. After writing P, we have to find P inverse. By using your calculator, we can easily find the inverse of matrix. After finding this, we have to consider P inverse into A into P. So P inverse means 1 by 2, 0 minus 2, 1, minus 2, minus 2, 0, minus 2, minus 2, minus 1 into A matrix. What is A matrix? 1 0 minus 1, 1 2 1, 1 0 minus 1, 1 2 1, 2 2 3. P inverse A into P. P matrix is 1 minus 2 1, minus 1 1 minus 1, 0 2 minus 2. So if you multiply these 3 matrices, we have to get a diagonal matrix D. So D, multiply these 2 matrices and the resultant matrix you multiply with this. All these matrices, the product is given by this matrix, which is diagonal matrix. Only the diagonal elements are non-zero, remaining all are zeros. We can observe here what are the eigenvalues for this matrix. 1 2 3 are the eigenvalues. So only those values we get in the diagonal form, one diagonal elements 1 2 3. So this is the diagonal matrix. Therefore P inverse into A into P is equal to, we got diagonal matrix. So we say that the matrix is diagonalizable. Thank you.